Welcome to this example, which is our in-class application on how to calculate a vapor pressure profile, where our example case, it's about the profile through an insulated roof. We have a multi-layered structure with roof slates. We have some wooden boards, and then we have the insulation. And as indoor condition, we have 30 degrees centigrade and this vapor pressure, 2,332, and outdoors another lower vapor pressure, and outdoors is 0 degrees centigrade. We have also to consider the exterior surface resistances for vapor and for temperature, for heat flow mostly, but also on the interior side we have the interior surface. So here, as our example gives us the resistances of all of these layers for thermal transport, for heat conduction, but also for the vapor, we have vapor diffusion resistances, the set values as we have over here. And we're going to use those to calculate the distribution of the vapor pressure. So we should find the temperature distribution. We have all the interfaces between the layers, as it's noted here. And also we should find the vapor pressure. And in between, we need to know something about the saturation value for the vapor pressure. So all this is a huge calculation in a way, so we'll put it in a table which I have over here on the whiteboard I have prepared. I hope you can read all the layers I've indicated here, and also the interfaces where we should calculate things. For instance here, SE/SL is the interface between the exterior surface resistance and the stone slates that we have, and so forth for the others. I've put here the same information as we have a column with the thermal resistances R. It's thermal, so it's red. And over here we have the set values here in blue, which also came from the information we got from the beginning. We have the interior and the exterior temperatures and also the vapor pressures. So it's a matter of distributing the temperatures, and later on we come to distributing the vapor pressures. Now, first of all, to calculate the distribution of the temperatures, delta T, if we take one layer, for instance the exterior surface resistance, then there is a temperature difference between what is the outside air and what is on the surface of the slates as we have. So such a temperature difference, delta T, it comes as a result of the resistance of that layer, in this case the exterior surface resistance, so the 0.04, in comparison to the total resistance, the sum of resistances for the whole construction. And when we calculate that, so I need that as a helping variable. I have here the summation. So the summation of all the resistances is 4.11 for all those layers we have. So that's a number I know for my calculations. And then that should be multiplied with what is the overall temperature difference over the whole roof. And that's 30 minus 0. So that's the interior surface, the interior room temperature, subtracted from that the outdoor temperature. That's our formula how to calculate delta T. And so if I say 0.04 divided by 4.11 and multiplied with 30 degrees as I have, then the temperature drop over my exterior surface resistance is 0.3 degrees centigrade. And I've cheated a little bit because I have calculated also that for the remaining layers that we have. And if I can remove this, then we can see the result for the temperature drop over all the layers. That means now that I can calculate the temperatures, so at the interface between the exterior surface and at the stone slate, so that means at the exterior surface of our roof, then we have 0 plus 0.3, so that means that in this position I have 0.3, and then I can say 0.3 plus 0.1, 0.4, 0.4 plus 1.5, and so forth. You calculate all the temperatures all the way through the roof towards the interior. Okay, given that information, well, then we're going to calculate something with water vapor. And therefore, we always need to know what is the saturation value for the water vapor pressure. This we can look up in a table, or we can use one of those formulas that gives us that calculation. So if we take at 0 degrees outside, then the saturation value for the vapor pressure is 611 Pascal. Here, like this. And likewise, I have calculated this for the remaining layers, or I've looked it up in a table. I just missed the value just here at the exterior surface is 624 Pascal, and so forth. So this is the number that we need to correspond with our moisture calculation. We got now, we're going to make the distribution between vapor pressure indoors 2,332 towards outdoors where it's 489. How to distribute that? Well, it goes along with a similar formula as we used before. I'll now make it blue. So we have for each layer, we have a drop in vapor pressure, which is equal to that layer's resistance for vapor diffusion. That's the set value. We should take that as a relationship to the total set value for the whole construction, like that. So therefore, I need to know what is the sum of set values for all the layers. I have that number. It's 7.56 times 10 to the power 9 in the units for the set value. So, and this we should multiply with what is the difference in vapor pressure between inside and outside. So we should have a multiplication with a parenthesis, P vapor inside, because that's the highest value, subtracted from that the vapor pressure outdoors, like this. So that's our formula, and the recipe is exactly the same. So we can calculate now delta P over the exterior surface resistance. Well, that resistance is a very small number in relation to the others for the vapor. So therefore, the delta P we get on the outside, it becomes very small. It's only 2 pascals out of the several, well, a couple of thousand almost we have. But with this recipe, then I can calculate for also for the other layers what is the pressure drop over each of the layers. And this I've also calculated beforehand, so you can see it here. I just corrected this because it vanished a little bit here. So now we have the drops over all of the layers. Now the recipe is the same. So we can calculate the vapor pressure at the interfaces, for instance, to calculate at the exterior surface of the roof, so the interface between the exterior surface resistance and the slates and as a roof cover. Then it's 489 plus 2. There we should have 491. And as you can see, I have calculated or put here to the whiteboard also the results for all the other layers. So that's good. And we should think that we are done and can put those results on our results sheet. But before doing that, we have to check if any of those results are too large compared to the saturation vapor pressure, because that is a maximum value that we can have. And so therefore, we are making a check. 489, that was the outdoor condition. That's good. On the exterior surface of the roof, we have 491. That's less than 624, so that's also good. 1,808. Gee, that's more than the saturation value, than the maximum possible. So now we are in kind of a problem, or we can solve it, because now we have to solve for another column here in my sheet here, which is the corrected value. We have to correct our values. First of all, we still have, of course, the same outdoor conditions. And here at the exterior surface of the roof, 491 was still good because it was less than the saturation value. But from now on, we have to make a correction such that we don't get values that are too high. The correction says that the value must never exceed the saturation value. So it seems that here we have something with condensation that would take place just on the interior surface of the slates or on the outside of the wooden boards in our roof construction. So when we have condensation, we cannot have a higher vapor pressure than the saturation value. So I put here 631, which is the saturation value I just put over there. Well, now, to make the correction, I need to distribute the conditions between 631, where I had the condensation to take place. I'll just bring that in here. And the interior vapor pressure, which was still, of course, the 2,332. And this distribution between those two positions, I have to take over only some of the materials in my roof. And that I have to consider those layers that I encircle here. So that's the wooden boards, the mineral wool, and the interior surface. Now, to make this distribution, I'm going to make a little bit of calculation of the same type, but I need to have a distribution only over 3 layers. So the summation of set values over here, if I take that number, is of course smaller. It's only summation of set value is 2.15 times 10 to the power 9, because we only have those layers. Now, to make the correction, if I want to calculate the vapor pressure in the interface between wood boards and mineral wool, well, then the equation would look differently. And I hope I can put it correctly down here in the bottom, and I hope the camera can follow me all the way down here. When I write that the vapor pressure at the interface between the slates, the wooden boards and the mineral wool, well, that becomes the vapor pressure I had just in the previous interface, which was the slates and the wooden boards. And then I should add to that, what is the increase I have over there? I have to look to the set value for the wooden boards. So that becomes the set value of the wooden boards. And then I should divide that by the sum of set values only for those layers that I have ringed in here. So that was wooden boards, it was the mineral wool, and it was the interior surface. And that I should multiply with the vapor pressure difference between the interior, which I had there, that was the 2,332, and then the point where we had the condensation, so the vapor pressure there, at the interface between slates and wooden boards. So that becomes my calculation to calculate delta P over the wooden boards. When I calculate that, that extra, then I get 701 in that position, and that is, well, that's still at condensation. So I get a higher value, but it has to be, cannot be more than 701. Next, when I go from and do the same calculation for the next, then I get 945, and 945 is less than 4,066. So this is good. And this way we can keep calculating all the way towards the interior. Now the result is, if we look back, I hope the camera can follow also on the slide over here, when I've calculated, then we see the result is that we got those vapor pressures. Some of them were too high compared to the saturation value, and then we made the correction as I just showed. We can also show it graphically. And in a graph, which I have here, then I've plotted along the abscissor axis here. It shows the cumulated set values for the layers as starting from the outside. So the set values, the set values with raised to the power 9 something. First, we thought we had a straight line kind of distribution of the vapor pressure. But when we also considered the maximum possible, the saturation value, which is the purple line we have here, well, then we saw that we got some values which were too high, and that is physically not possible. So what we did then was that we started from the outside and we tried to calculate if it were too high. Then we reduced it until the saturation value. Then we tried again, but it was also too high, and then we put it to the saturation value. And this way you keep correcting and correcting until you finally get a final corrected vapor pressure distribution from inside to outside, but never exceeding the values for saturation vapor pressure. So this kind of concluded the long story about how to calculate vapor pressure distributions and considering the risk of not having, or if you have condensation, how to correct for it. So thank you for this.